Class, welcome back to another video. Today we move on a little bit to 5.6. And really, what we're doing here, we are teaching you another method that we might need to use to solve exponentials and logarithms, okay? And it's called this, a substitution. In calculus, you might see U substitution. It really doesn't matter the letter that you use, just you know that we're going to be substituting. And really, guys, what's going to happen is we're going to get stuck in a little bit, and what we're going to have to do is we're going to have to set what we're stuck with into its own separate equation, because that will allow us to substitute, allow us to solve, and then once we solve the easier equation, we'll be able to plug in that hard part back in. Okay, so on this first problem, what I want you to understand, like if I see two exponents, different bases, I want to still try to see if I can get them to have common bases. All right, so I would say I could change this 4 into 2 squared, and then this. Okay, this part I think we're okay with, or at least I hope we are. Right? I see 2 to the 2x, I see this 2 to the x. I now have common bases. Here's the problem though, guys. I mean, if we wanted to solve this exponential, we would need to get this into a single exponential, and then that exponential would have variables in the numerator, and we would be able to switch it to log form and solve. How am I supposed to get this into a single logarithm though, when I don't have any rules for common bases with subtraction between them? All right, so this is what I'm talking about. We are stuck now. I don't know what to do. But I do. Because what we can do is we can recognize that this 2 to the 2x is actually the same as 2 to the x squared, right? If I have an exponent of 2x, I can break it up however I want. I can do 2 to the x first and then raise it to the second power. And hopefully you guys are seeing what I mean by this substitution business. I see a 2 to the x here, I see a 2 to the x here. So this is what I'm talking about with a substitution. I'm going to come over here and I'm going to say, well, I'm going to set a equal to 2 to the x. This exponential that I couldn't do anything with, that's going to be my a, my new function. Alright, and now I'm going to completely replace it, because now if a is 2 to the x, well then this is a squared, this is a, minus 12, and oh my gosh, we know what to do. At least I hope we do. I now have turned some crazy looking exponential into a quadratic. So we factor. Let's see here, minus 4 plus 3, so a equals negative 3 and 4. Alright, now this is where you need to understand you are not done. You are not done. There is plenty more work to do. Because what? Negative 3 and 4 are not my values for x, which is what we're trying to solve for. They are my a values. So now, guess what we have to do? If you said plug in these a values back into the original a function, well then you were correct, okay? Because I absolutely need to do two different equations now. I'm going to come over here and I'm going to say, well, negative 3 has to be equal to 2 to the x. And I'm going to come over here and I'm going to say 4 has to be equal to 2 to the x. And you know what, actually, guys, I'm going to write this in the other way. I'm going to move my negative 3 over here. I'm going to move my 4 over here, just to kind of stay consistent with what we like to see. Alright, because now I have an exponential, variable stuck in the exponent, so I can create my log, or convert to log form, I should say. So log, oh my gosh, log base 2 of negative 3 is equal to x. Uh-oh, can't have a negative argument. Nothing from that one. Over here, if you want, you could convert to log form, or you could just recognize what's easier, common base, right? All right. So again, what did we do? The first thing we had to do is we had to recognize and try to get this into something that we could solve for. But what we needed to understand is that there was no way to turn this into a single exponent. So we needed to use this a substitution. All right, we needed to kind of get rid of the nasty part for a little bit, solve a way we did know, and then go back and find our x values. All right, so that is what we're going to practice today. We're going to do a few more. They're all going to work very similarly. So on this one, I would start, let's move the 2 over, right? So we have e to the x minus e to the negative x equals 10. I like it. Yikes. I can't combine them. Let's see, what could I do? I could do this just to kind of help me understand what I got going on here. One thing I would strongly encourage you to do, make sure before you substitute, before you use this a substitution method, that you get both of your pieces to look identical. Like right here, I wouldn't really know what to substitute because these two things aren't completely identical. But if I change this, e to the negative x, into 1 over e to the x, well, now I have e to the x. So what do you think we're going to set as a? Hopefully you said e to the x. All right, because now I'm just going to completely replace any e to the x with a. A minus 1 over a equals 10. One thing I would strongly encourage here is get rid of the fraction. We know that to get rid of a denominator, we can just multiply the entire thing by that denominator, right? So if I do this and I multiply by a to everything, please remember you got to distribute it everywhere. You're going to get a squared minus 1 equals 10a. And with a little rearranging, I think we have another quadratic. A squared minus 10a minus 1 equals 0. All right, now unfortunately we cannot factor this one, but we do know the quadratic formula, and that's what we're going to try now. So a is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, good. This is easy. We got this. A is equal to 10 plus or minus the square root of, be really careful, negative 4 and negative 1 is positive 4, so 104 all over 2. We continue. Again, guys, when you get to the square root of 104, the trick is, and the idea is, and if you want to do your factor trees, go for it, please, whatever is easiest for you. I know right now that I can take a 4 out, and I think of money, right? I know that 100 is easily divisible by 4, right? 25 times. So I know that 104 would be divisible by 4 as well, but 26 times. So I immediately know that I can say a is equal to 10 plus or minus. Now be really careful. It's the square root. If I take out, or if I can factor out a 4 from 104, remember that I'm taking the square root of it. Like, that's the whole reason that I want to take out a perfect square. So I'm going to have 2 square root 26 all over 2. And now when I break this up, I'm going to end up getting a is equal to 5 plus or minus root 26. Okay, so hopefully we're good at getting there. Now you have to remember, we are not done. You need to set that equal to our original a, which is e to the x. So 5 plus or minus root 26. And let's see here. Well, to solve this, I see my variable in the exponent, so I would want to convert. So let's go ln, right, because we have base e. So ln of our argument 5 plus or minus root 26 is equal to x. Okay, now at this point in time, guys, you just basically need to check for extraneous. Are both of these okay, or was one off? Something like that. And what I would hope you understand is if you have 5, a positive 5, and you add anything to it, you're going to be okay. So my plus route is perfectly okay. Without using a calculator, I would want you to be able to understand that the 5 minus root 26 is not okay. And how did I know that? Well, because the square root of 26, right? The square root of 26 is greater than the square root of 25. All right? And what is 25? Square root of 25, I'm sorry. That's 5. So if I had 5 minus square root of 25, it would be exactly 0, which we can't have already. But I know that square root of 26 is even bigger than the square root of 25. So of course 5 minus square root 26 is going to be negative, which means it is not a viable option. We must say that x equals ln and only the positive option. All right. Okay, let's check out another couple and see how we're doing on these. Okay, so next one is extremely similar to the one on the page before. No e's, but still exponents. Let's see what we got here. Okay, so we can definitely start by moving that 2 over. So 3 to the negative x equals negative 4. And then again, I want to make these at least look the same to see if I can do anything with them. 3 to the x minus 1 over 3 to the x equals negative 4. Uh-oh, I'm stuck again, right? I can't do anything with these exponents because I don't see multiplication or division. All right, so I'm stuck unless I use some a substitution. So let's go for it. All right, I'm going to substitute a for 3 to the x in a couple of places. That should help me. Let's try it. A minus 1 over a equals negative 4. And then if you remember my next step, I want to get rid of that denominator. I don't want fractions. So I'm going to multiply everything by that denominator, which will clear it. Because now I have a squared minus 1 equals negative 4a, and oh my gosh, I have another quadratic. Perfect. Now, maybe not perfect, because I still have to use the quadratic formula, but something that we can do. All right, so here we go. A is equal to negative 4 plus or minus the square root of 4 squared, so 16 minus 4 times 1 times negative 1 all over 2 again. All right, we keep going. Negative 4 plus or minus the square root of 20 all over 2. Okay, square root of 20, I can take a 4 out of 20 as well. All right, so I'm going to say that this is a equals negative 4. And guys, what I'm going to actually do this time, just to kind of make sure that we don't mess up or forget, I'm going to break up this fraction now. All right, I'm going to say it's negative 4 over 2, plus or minus, and then let's see, square root 20, we said is 4 and 5. Okay, so 2 square root 5 also over 2. Which is pretty nice, because then we can say that a is equal to negative 2 plus or minus root 5. Which is great, but please remember, you are not done. You need to set the original, right? Or we need to substitute back in now into our a function. So 3 to the x equals negative 2 plus or minus root 5. And let's see here, I would want to change to log form because my variable is stuck in the exponent. So I would say log base 3 negative 2 plus or minus root 5 is equal to x, and please just make sure you check for extraneous solutions. Very similarly to the last problem, I'm not going to be okay with one of these. All right, one of these is not going to work. The reason is because I have a negative and I'm taking away more, right? So negative 2 minus root 5 is going to be a negative, and you cannot have a negative argument. So I already know that the minus routes out. How about the plus? Can we get to positive? Yes, we can. Square root of 5 is 2 point something, right? I don't even necessarily care what it is. I just need to know that it's bigger than 2. Because if it were exactly 2, then I would have an argument of 0. But because root 5 is bigger than 2, it's going to get positive, and we like that. That is all good in my book. All right, so we now know that our x value is log base 3 of negative 2 plus root 5. All right, last one, almost done. This one I would say very similar conceptually, but you're going to have even more work to do before we substitute. And a little bit tougher, you have to think a little bit more outside the box in terms of your exponent rules. Now, I see a 9, I see a 3, I want my base to be 3. So I'm going to say 9 to the x is the same as 3 to the 2x. Okay, what did I do there? I basically said 9 is 3 squared, and I know that if I have 3 squared to the x, it's just 3 to the 2x because of our power to a power rule. This is where I'm nervous. I'm nervous because I just need you guys to remember your exponent rules. If you have 3 to the x plus 1, you need to be able to go backwards and say, if I see a single exponent, or excuse me, a single exponential with addition in the exponent, well, I can separate that using multiplication. All right? So really what I'm seeing here is I'm seeing minus 3 to the first times 3 to the x, right? If I see common bases, I can add the exponents together when they're being multiplied, I should say. Okay? So now, what's going on here? I would even go further and say this is 3 to the x squared minus 3 times 3 to the x plus 1 equals 0. Well, what am I going to put as my a? You guessed it, 3 to the x. So now I have a squared minus 3a plus 1 equals 0, and we are right back at it with our quadratic formula. A equals negative b plus or minus the square root of, okay, so 9, b squared is 9, minus 4 times 1 times 1, so just minus 4 all over 2. Okay, so this one, I don't even have much work to do here. 3 plus or minus root 5 all over 2. And I'll just leave it right like that. Okay. So, last thing we have to do, we have to recognize we are not done. We are not done. We have our a value. We don't want a, we want x. So you need to plug what we got for a into our a function, all right, or a equation. So now I'm going to say that 3 to the x, right, because that's my a, is equal to a. So 3 plus or minus root 5 all over 2. So when we do when we recognize that our variable is stuck in the exponent, we're going to try to go to log form, which means I'm going to say log base 3, and then this becomes my entire argument, 3 plus or minus root 5 all over 2 equals x. And you guessed it, guys, the last thing you have to do is check for extraneous. All right? I know that everything's going to be okay as long as my argument is positive, right? So 3 plus anything, and then divided by 2, you're going to be okay. All right? So the positive, we're good. We're good. The minus is the one that we have to check for. And really just think, you know that you need to have 3 minus root 5 be positive in order for this to work out. So if we think about this, and we already said it, the one above, root 5 is a little bit more than 2, right? How do I know that? Because root 5 is really close to root 4, and root 4 is 2. So 3 minus 2 point something is still positive, and a positive divided by a positive is a positive, so guess what? There are no extraneous solutions. We would box both answers, or we would leave it as plus minus root 5 over 2. All right, I think that's where I'm going to stop my video. I would like you guys to continue on and try the last two problems on page 31 on your own. This first one up here is like a review. Okay, this is something that we've already been doing, so yes, I want you to do this one just to practice again. This one down here, this is the new concept. This is the new material. I really, really, really want you to try this one before class tomorrow. All right? So, or actually not tomorrow, next week. I hope that this is making sense. I hope you understand why we have to do this, right? We get stuck because of our different exponent rules. We can't just use our the same rules that we've used in the past. So that is why we need to use this new method for helping us solve equations. All right? I hope you have a great day. I'll see you next time.